Hello and welcome everyone to our presentation. My name is Rohit Sah. Today, me and my team is going to present a research work titled Accelerated Nested Virtualization with HyperTurtle. Moving on with the abstract part. In simple terms, we are trying to fix the huge slowdowns that occur when we try to run a virtual machine inside some other virtual machine, something that is becoming more common in clouds and secure containers like Kata. Nested virtualization. We are dealing with three layers: the L0 layer or the physical hypervisor, bare metal layer, L1 layer, the guest hypervisor, and the L2 layer, the nested VM. Every time the L2 layer needs to do something important, it has to call upstairs, which means bouncing between layers L2, L1, L0, and then back. These world switches are like context switching nightmares, slow and costly. With the problem part, each world switch takes about a microsecond. So 30% or more of the CPU time just goes off into switching overhead. For example, handling a single EPT fault takes 6 world switches instead of 2, and multiply that by thousands of faults during boot time and the nested VM crawls. So these are the performance overheads in the nested virtualization that I just mentioned. The multiple context switches and the world switch overhead and the EPT faults, which leads to performance degradation. So this is the case of vanilla nested virtualization EPT fault. So a fault triggered in L2 that will lead us to L0 hypervisor, which will in turn call the L1 hypervisor, and after resolving, it will redirect back to the L0, and finally the call goes back to L2. Now we will move on with some prior work that has already been devised. Direct virtual hardware bypasses L1's IO stack for speed, but kills L1's control. SVT co-schedules L1 and L2 threads, but it depends on special CPU features like SMT. Software tricks like X containers or PVM works, but they are messy and intrusive. So existing solutions either tie you to a specific hardware, break compatibility, or remove control. So there comes the limitations, which I already mentioned. And finally, the proposed solution, which is the HyperTurtle. The key idea of HyperTurtle is pretty simple. Take the L1 operations, which are the most frequent, and run them directly into L0. How? Using eBPF programs. So instead of bouncing between L2, L1, and L0 multiple times, L0 just runs a small verified eBPF program on behalf of L1. So it leads to fewer context switches, same control, and no kernel hacks. And what are the results? Up to 5x times faster EPT fault handling and 27% faster Kata container boot times. So here, an EPT fault resulting into L0. L0 will not go to L1, but instead it will do the L1's part in through the hyper call and then directly goes back to L2, thus reducing the context switch between L1. Now we will move on to the background part. Nested virtualization. Here is what is happening under the hood. L0 emulates virtualization extensions for L1. That means every privileged instruction from L1 or L2 gets trapped and reinterpreted. Each of those traps flushes CPU pipelines and translation caches. So the key point is, more the layers you have, more switches you need. eBPF, the secret weapon. eBPF or the extended Berkeley packet filter lets us safely run custom code inside the kernel. It is verified before execution, sandboxed, and extremely fast. Think of it as a programmable hook right inside the OS. That's what allows HyperTurtle to offload L1's logic safely into L0 without rewriting the kernel. And lastly, the Kata containers. Kata containers mix container agility with VM isolation. Great for security, but they rely on nested virtualization. What's the catch? They can be 3 times slower than regular containers. But HyperTurtle cuts that overhead drastically, making Kata containers nearly as fast as normal containers while keeping VM-grade security. So from here on, we will move on to the analysis part of the research work. This will be taken over by my friend. Thank you, and this is my part.
Hi, I'm Aditya, and I will be explaining the analysis part of our research paper on HyperTurtle accelerating nested virtualization. We will analyze the performance impact in 3 important cases: EPT fault handling, networking, and profiling. Before this, we understand about the world switch cost. World switches occurs when the CPU transitions between layer L0, L1, and L2. For example, when L2 executes a pre-release instruction or performs an I/O operation to a hypercall. Each world switch requires the CPU to flush its pipelines, save all VM registers to the VMCS, and load the hypervisor register again. These operations have significant overhead, about 33% of a 10 microsecond instruction emulation, as shown by the Villanova. What is the takeaway from this? World switches are expensive and their latencies varies depending on their cause. They are more expensive when triggered from L2 than from L1. Now let's discuss about the EPT faults. Memory management is one of the main reasons for the performance loss in the nested virtualization. Each extra virtualization layer triples the number of world switches needed to handle the EPT faults. In the nested setup, L0, L1, and L2 each maintain their own mapping. But since CPU don't support 3 level page walks, L0 must shadow L1 mappings and build a combined translation table from L2 to L0. The mapping page table hierarchy is shown in the image, how they are arranged. Now let's discuss about what happened when L2 encounters EPT fault due to missing mapping 0 to 2 in page table entry, which triggers a VM exits to L0. Then L0 checks if a valid mapping appears in the EPT 1 to 2. If it is missing, L0 injects the EPT fault into L1 and enters L1 immediately thereafter. L1 handles the EPT fault by mapping the address in the EPT 1 to 2, and then L1 tries to resume L2 and trapping again into L0. L0 enters L2, which re-executes the instruction that triggered the EPT fault. Since the EPT 0 to 2 mapping is still contained in present entry, another VM exit occurs. Then L0 once again walks the EPT 1 to 2 mapping and finds the entry and fixes the EPT 0 to 2 mapping with the value from EPT mapping 1 to 2. Then L0 re-enters L2, resume the execution. This procedure requires a total of 6 world switches compared to only 2 in the non-nested virtualization. We measure the EPT fault latency incurred by the VM when faulting in 1 GB of consecutive memory with or without nesting. We observed that the nested EPT fault experienced 5.1x and 5.3x latency increase over the non-nested scenario for the average and 99p latencies. EPT fault occur most frequently early in the VM lifecycle because memory has not been allocated yet. Therefore, the EPT fault handling performance directly impact the startup time, thus requiring the low startup latencies. What are the takeaway from this? EPT fault handling introduce major overheads because of the repeated bulk switches, significantly slowing down the startups in the nested virtualization. Next, talk about the networking part. Let's talk about networking in the nested virtualization. In the nested setup, L2 virtual machines must communicate with the outside world via L0, which manages the physical NIC. There are two main approaches for this. That is the nested VirtIO and the direct assignment. In the nested VirtIO, L1 acts as a mediator between L2 and L0. L0 provides a virtual NIC, NIC01 to L1, and L1 then creates another virtual NIC12 and exposes it to L2. Basically, L1 forwards all the traffic between NIC01 and NIC12. If we talk about the direct assignments, in direct assignment, L0 can expose NIC directly to L2. This allows NIC01 to connect directly to L2 and completely bypassing L1. The key ideas here is that L1 is no longer in the data path. If we compare our performance, direct assignment is clearly better. In latency terms, latency decreases by around 40% for the mean and 37 for the 99 percentile, and throughput improves by about 44 percentile in case of direct assignments. Why? It's all about world switches. In nested what I require three world switches to send a single packet, and direct assignment only requires one world switches, reducing the overhead significantly. Next, understand how the flows are there. In the nested what IO, L2 executes the MMIO right to notify the NIC12 of the sending pending packets, which triggers VM exits to L0. Then L0 injects the VM exits to L1 hypervisor, which forwards L2 request to NIC12 what IO worker threads. The latter tries to transmit the packet. Next, triggering a VM exits from L1 to L0 due to a similar MMIO write. L0 hypervisor forwards the request to NIC0 on what IO worker, which send it via physical NIC. Next, talk about the direct assignment, which is much shorter. In direct assignment, L2 executes the MMIO write to notify NIC02, which triggers VM exits to L0. Then L0 what IO workers send the packet via the physical NIC. Now this is the results soon. Uh, Comparison about nested what I direct assignment, we can see that the direct assignment performs better as compared to the nested what I. Next, talk about the profiling. Application profiling. Profiling is broadly used to find a bottleneck in the development and production system, with some vendors such as Netflix and Google continuously profiling their production application. Sampling profilers periodically interrupts a program and samples the program state, as well as hardware performance monitoring counter PMCs. Each sampling event begins with an interrupt caused by the overflow of PMC, which counts cycles since the last event and the ends when the profile program resumes executions. Here, the profiler sampling latency in different settings are shown, where L0 to L1 is very less. If we talk about the L1 container, it is approx 5 times as compared to L0 to L1, and L1 to L2 increase significantly higher. Next, talk about the uh, sequence of event that occurs when profiling a container and a nested virtual machine from the L1. See, KVM emulates the HW counter by exposing the virtual registers. L0 traps the L1 when latter tries to access them. Now let's understand the flow is as follows. Uh, First, we are discussing about profiling a container in L1. The HW counter triggers an interrupt, which triggers a VM exit to the host L0. Next, the host injects a similar interrupt to the L1 and enters L1. As part of interrupt handling routine, L1 reprograms the HW counter and performs the multiple access to the MSR, bringing the total world switch count to 18. Next, talk about the profiling in Kata container in L1. In this, the HW counter triggers an interrupt, which triggers an exit from L2 to L0. Then L0 injects a similar interrupt to L1 and enters L1. Next, as a part of interrupt handling routine, L1 reprograms the HW counter, access the MSRs, perform the VM read and VM write, which access the VMCs, and overall triggering 22 world switches. Then L1 executes the VM enter instruction, which triggers and exits to L1. Then L0 emulates the VM enter instruction and enters the L2, which brings the total number of world switch to 26.
Hi, my name is Sachin and I'll be covering design and implementation part of HyperTurtle. HyperTurtle was built with four main design goals in mind. First, performance, to eliminate excessive world switches. Second, control, so that L1 can still enforce its policies on L2. Third, non-intuitiveness, meaning we aim to minimize modification to L0. And fourth, generality, so that the approach can be applied to minimize various OS subsystems, not just one. To achieve this, HyperTurtle removes some part of L1 functionality into L0, reducing world switches. It uses hyper-up calls, which are eBPF programs, allowing L1's logic to safely run inside L0. This ensures that while performance improves, L1 retains the full control over L2. Because eBPF supports already exist in L0 kernel, we only need small modification, mainly exported nested virtualization information through helper functions, and adding an installation mechanism for L1 to upload eBPF program. Finally, HyperTurtle's modular design allow it to be extended to different subsystems.
To enable efficient communication between L1 and L0, HyperTurtle replaces packet-based switching communication with shared eBPF maps. These maps allows concurrent access to shared data, a key improvement over previous methods. A new hypercall is introduced that creates a shared memory, PCI devices. This device exposes array-type eBPF maps from L0 to L1, allowing both layers to exchange information efficiently. Hyper-upcall registration. For hyper-upcall registration, L1 first uploads the eBPF program via a hypercall and then links it to specific hooks in L0. This registration process is split into two parts, loading and linking, which allows flexibility and reusability across hooks. HyperTurtle supports two security models, L1 provided eBPF, which are verified by L0 eBPF verifier to ensure they are safe to run. Vendor vented eBPF, which are only loaded if they are signed and verified, typically by a cloud vendor. Both models guarantee that eBPF can only access their own L2 and memory space, ensuring strong isolation between tenants. One of the most important design challenges in HyperTurtle is handling EPT fault handling efficiently. When an EPT fault occurs, the system must manage shared state between L1 and the eBPF hypercall running in L0. This involves handling memory allocation, race conditions, and consistency of mapping between L1 and L2. Because eBPF program cannot dynamically allocate memory, HyperTurtle uses a pre-allocated memory. If that pool becomes empty, the system falls back to normal EPT fault handling mechanism. The pool is refilled either asynchronously or in batches by L1. To maintain consistency, new mappings are logged into a cyclic fault log, which L1 later reads through synchronize its page table. If this log becomes full, the mechanism again falls back to the default path. To ensure synchronization and coherence, the CRC register is shared, allowing the hyperupcall to verify existing mappings. Locking mechanisms are used to prevent race conditions, and if a lock fails, the system safely falls back to the normal handling path. HyperTurtle also ensures coherent mapping between L1's memory and hyperupcall using file-backed memory through VirtuoFS. The process involves 5 main steps. First, acquiring a log. Second, check existing mapping. Third, handle the fault. Fourth, log the L2 physical address. And fifth, have the VMM prog on log on the next VM exit. Together, these steps keeps the page table of L1 and L2 consistent. The EPT fault hypercall is hooked directly into L0's EPT fault handling. When L0 detects a missing entry in EPT 1 to 2 mapping, it triggers the hyperupcall instead of forwarding the fault to L1. The hyperupcall then allocates a new frame, updates the mapping, and resumes L2's execution, effectively skipping several word switches. Inside the eBPF program, the logic works as follows. It first checks L1 page table for an existing mapping. If one found, it returns it immediately. If the fault has been logged externally, it follows the normal EPT path. Otherwise, it allocates a new frame from the pool, updates EPT 1 to 2, and the fault log and resumes normal execution. Networking. HyperTurtle also improves nested network performance while keeping L1 in control. Normally, direct assignment provides high performance but removes L1 control. HyperTurtle fixed this by letting L1 install eBPF-based hypercall into L0 network stack. This combines the speed of direct assignment with L1's ability to manage network policies. To achieve this, 3 design steps are followed. First, share information using eBPF map for configuration and monitoring. Second, hook into L0, attaching eBPF program to its virtual network interface. Third, develop the eBPF program themselves. Examples include a simple pass-through that forward packets, a stateless firewall that filters packet by source IP, a rate limiter that caps traffic based on limits set by L1, and a TCP top program that monitors all TCP connections. This is the networking eBPF data flow in the L2 data path. Application profiling. The final subsystem, HyperTurtle accelerates its application profiling for nested guests. Traditionally, profiling involves multiple word switches from L2 to L1 to L0, which adds latency. HyperTurtle moves the profiling logic L0 through an eBPF hypercall, allowing it to collect performance data directly and with the core override. The design again follows the same three-step approach. First, it uses a shared eBPF map as a ring buffer to store profiling samples. L1 periodically empties this buffer, keep logging continuous. Second, the hyper call hooks into the existing Linux perf subsystem for sampling events. Third, an eBPF program runs in L0 periodically sampling the guest context like its instruction pointer at the given frequency. We also introduce a helper function called vCPU probe, which lets L1 easily inspect the state of L2 virtual CPUs. This approach achieves both low latency and isolation, since profiling runs only when the process is in cache mode, ensuring no cross-VM data leakage. To summarize the implementations, HyperTurtle requires only modest code modifications, mainly in KVM, kernel's eBPF subsystem, and KMO. Most complex components like EPT fault hypercall require around 560 lines of code, which shows how lightweight the solution is compared to its impact on performance. Now the evaluation part will be covered by my friend Sayan. Thank you.
Hello everyone, I'm Sayan Mandal. I'll be continuing the rest part of the presentation. So till now what we have seen, we have seen that what is HyperTurtle, how HyperTurtle is designed and implemented in modern operating system, and what is the use of HyperTurtle. So now the time has come to see its performance by testing it on a physical machine. So the machine in which we'll be running all the benchmark is this machine. So whose hardware specification you can see here and the software specification you can see here. So all the graphs and the result that I'll be presenting in my upcoming slides will be based on this setup. So now coming to the first micro benchmark, which is EPT fault handling. So our main goal is to evaluate HyperTurtle's memory management optimization. So for that, we create a 1 GB byte of kata container to measure the EPT fault latency, and we have tested that, and the result that we got is displayed here. So we can see that the memory access time has been increased by 5.25 times on for an average case, and for 99 percentile times, that is in the worst case, the memory access time has been increased by 4.76 times, which is only 8% slower than non-nested baseline. So why this is happening? Because we are avoiding repeated while switches. So if we see this, so this bar shows the nested virtualization without HyperTurtle, and this is also nested virtualization with HyperTurtle, and this is means normal virtualization, means not a nested one. So you can see that by using HyperTurtle, the performance gain you can see it's around 5.26 times, which is nearly same as a non-nested virtual machine. So and the similar result is also visible in case of 99 percentile. So now coming to the next benchmark, which is for networking. So for networking, we'll be comparing this four model. That is, the first one is the nested virtualization, and the next is your direct assignment. So in direct assignment, the main problem is that the L1 layer was losing control over L2. So in order to restore L1's control, we have introduced HyperTurtle. Now you can see that there are two versions of HyperTurtle, that is with firewall and without firewall. So when we have tested this, so the result we have got is displayed here. So here you can see that the average latency for normal nested virtualization, it went from 90 microsecond to 55 microsecond, so which is a improvement of 1.6 times. And for throughput, you can see that for a normal nested virtual machine, the throughput has increased from 12.1 Gbps to 17.3 Gbps. So it is a 1.4 times improvement. And when we add firewall in the normal HyperTurtle, you can see that it is a bit slower than normal HyperTurtle, but it's still comparable. The difference is very much negligible. Now coming to the next benchmark for application profiling. So if we do any kind of application profiling in the L2 layer, it comes with a lot of latencies. So in order to avoid that, we have implemented HyperTurtle. So now when we have tested that on the physical machine, so we can see that it is handling by 7.15 times faster, okay, and which is only 16% slower than normal native profiling. Okay, so you can see here also that is the latency. So this is the normal nested latency without any kind of HyperTurtle, and the same configuration with HyperTurtle is displayed here. So you can see the difference clearly. Now coming to the micro benchmark for system boot and workloads. So you can see that for Kata containers, for 4 KB pages, it is 27% faster, and for 2 megabyte pages, it is 8% faster, and for Redis, it is 55% faster. For Death Star page, it is 35% faster. For NGNX, the throughput has increased by 45%. So you can see that from 1.24K queries per second, it has increased to 1.8K queries per second. And for Redis also, the improvement in throughput has been seen as 65%, and for memcached it has an improvement of 72%, and which is only 9% slower than your direct assignment. Now the evaluation matrices that we have seen in the last slide for NGNX. So you can see that this is the throughput for your normal nested virtualization without any kind of HyperTurtle optimization. Okay, and here the throughput you can see, and this is for the HyperTurtle one. Okay, and this is for that or direct assignment. So you can see that by using HyperTurtle, we have reached near about to the direct assignment. And what was the main problem of direct assignment? In direct assignment, L1 was losing its control. So by using HyperTurtle, we have restored the L1's control, and also the performance is also comparable. And similar result is also seen in case of Redis. Now coming to the evaluation metrics of the memcached. Okay, so this is the direct assignment curve, and this is the nested virtualization with IO, and this is the nested virtualization with firewall. Okay, so sorry, I mean without firewall. Now for this direct assignment, you can see that the latency is less, and this is the normal nested virtualization with the firewall, and it has a quite a high latency. And by using HyperTurtle, we have increased its performance near to the normal direct assignment. So you can see that there is a high gap, so this shows a high improvement. So basically why it works, so I think the major performance gain from reducing the wall switches. Okay, so initially because of the wall switch, all the latencies and all the problems were happening. So by eBPF hyperup calls, we have allowed L0 to execute L1's logic safely, keeping L1's control. So the L1 is fully controlling the L2 via L0. So the overhead is only when the fallback to L1 is required. And so these are the so in this way the means the concept of HyperTurtle has been achieved. And I forgot to say one thing, that is it is a software only solution by achieving hardware like speed. That means we are not changing anything in hardware, but still we are getting a huge improvement by changing a software level. That is by changing 1,000 line of code, we have improved to such a high amount. Now coming to the limitations. So eBPF can't handle complex IO and blocking system calls. Okay, and so some operation still fall back to L1, and for huge pages, this HyperTurtle concept is not efficient. Okay, so these are the major limitations, and these are mainly the engineering constraint and not any kind of conceptual flaws in the concept of HyperTurtle. So this concept of HyperTurtle is not only used in virtualization but can be used in the other fields also, such as networking, storage, smart NIC, and scheduling. And so HyperTurtle bridges the gap between the performance and isolation in nested virtualization by achieving near native speed without any intrusive changes. So this is basically the everything that we have done. So now coming to the conclusion. So if we recall that what was the problems, the main problem was nested virtualization suffers high overhead from wall switches. So in order to solve the problem, we have introduced HyperTurtle, which executes the L1 logics in L0 via eBPF hyperup calls. So this implementation was done across kernel, QEMU, and eBPF module by writing 2.6 thousand lines of code. Okay, and by changing this, we have improved a huge performance gain, that is 5 times faster for extended page fault handling, and 27% faster for container boot, and up to 65% higher app throughput, I mean application profiling. So what is the main outcome? So the main outcome is retaining L1 control and providing strong isolation, and it achieves near native performance, and it is very lightweight, general, and safe. So basically HyperTurtle bridges the gap between the speed and isolation in nested virtualization. Okay, so that's all from my team. So I hope you have enjoyed our research work and the explanation by me and my team members. And once again, thank you so much for watching the video.